motion, important equations. In simple harmonic motion, acceleration is always towards the center. Acceleration is proportional to the displacement from the center. So we can write the equation, initial equation A equals minus omega squared x, first equation. So we can conclude F force equals minus m omega squared x. Then this x displacement from the center, x equals a sine omega t. So here a is the maximum displacement from the center, capital A, amplitude. Then velocity v equals a omega cos omega t, fourth equation. There's another equation for velocity, v equals omega root a squared minus x squared, fifth equation. Then for time period t equals 2 pi over omega and frequency omega over 2 pi. Then for simple pendulum, this is a simple pendulum. If the length of the pendulum is L, length of the string is L, t equals 2 pi root L over G. That's our sixth equation. And at the same time, we have vertical motion spring, time period t equals 2 pi root m over k. And then we have another equation for total kinetic energy and total potential energy. Total potential energy, when if the spring is completely stretched, potential energy equals half k x squared. X is the displacement from the center, k is the spring constant. And in some equations we can use k as force constant, right? And at the middle of the motion we can conclude the potential energy is equal to the kinetic energy, and the extreme end potential kinetic energy is equal to the potential energy. But at the same time we should know the total energy is a constant always, right? These are the equations we have in basic equations we have in simple harmonic. We have two types of waves, stationary waves and progressive waves. Only from these two we have equations. So initial progressive wave equation is v equals f lambda, very basic equation. V is the velocity of the wave, f is the frequency, lambda is the wavelength. Stationary waves, we have three types of stationary waves. Stationary waves, stretch string, and then stationary waves in a closed tube. These are sound waves, longitudinal waves. And third one, again open tube, sound waves. Fundamental equation for stretch string, f naught equals 1 over 2L root t over m. Here root t over m is the velocity of the transverse wave in a stretch string. So this is our second equation. Then the third equation, fundamental frequency, and then fundamental frequency of open tube, f naught equals v over 2L, and again fundamental frequency of an open tube, f naught equals v over 2L. So this is closed tube and this is open tube. Then when a stationary wave is formed, we get a loop like this. So length of this loop is lambda by 2. Remember, length of a loop is lambda by 2, half of the wavelength. Then from stationary waves we get overtones. For stretch string we get f naught, 2f naught, 3f naught, 4f naught. Likewise we get all the harmonic values as overtones. But remember, in closed tube we get f naught, 3f naught, 5f naught overtones. We don't get 2f naught, 4f naught harmonics as overtones. So that basically goes f naught, 3f naught, 5f naught, 7f naught, likewise. And again, open tube, we get all the frequencies f0, 2 f0, 3 f0, 4 f0. Remember that. Right. These are the equations we get from stationary and progressive. In sounds, we have three types of questions: intensity, Doppler effect, and sonic booms. So if you are moving to intensity, in intensity, the initial equation we are getting is intensity equals power divided by area. So there's a modification for this equation as well. So power divided by area. If we consider this object, the source is as a point object, so the distribution of sound, yes, it goes with the shape of spherical shape. So we can consider the total area is area of a sphere, so it's power divided by 4 pi r squared. So from this we use this equation as well. I, intensity, is proportional to 1 over r squared. R is the distance from the center of the initial sound source. I proportional to 1 over r squared. This equation also very useful when you are doing questions. Then intensity level. Intensity level, L equals 10 log I divided by I naught. Here I naught, method of hearing, 10 to the power minus 12 watts per meter square. Right. The next part is Doppler's effect. Doppler's effect, if there's a relative motion between a source, between an observer and a source, that means relatively if these two are moving towards each other or away from each other, somehow if there's a relative motion between them, there's a change in frequency of the sound. So f naught will change to f dash. So that is Doppler's effect. So very basic equation is f dash is equal to velocity of sound relative to observer divided by velocity of sound relative to source into initial frequency or the original frequency. Sonic boom. Sonic boom occurs when the velocity of the source, sound source, is greater than velocity of sound. Right here, there are two equations we need when we are doing these questions. The sine theta value, we call this the half angle, is equal to velocity of sound divided by velocity of the source. And then again, Mach number is equal to velocity of source divided by velocity of sound. So these are the equations we need when we are doing sonic boom questions. Type of questions from interference. Interference is the overlap of two waves that is moving towards each other. So here we get two types of two waves moving towards each other. When they overlap, we get constructive interferences and destructive interference. So when constructive interference happens, we get an antinode, and destructive interference happens, we get a node. From these, we hear beats. So beats frequency is equal to, say, frequency of this is f1, frequency of this is f2. Beat frequency is equal to f1 minus f2, the difference between them. Right. These are the basic equations we have from simple harmonic motion and waves lessons. So let's quickly wrap up the equations we have. Simple harmonic motion, we have a equals minus omega squared x, and then we have x equals a sine omega t, velocity v equals a omega cos omega t, and again we have velocity equation v equals omega root a squared minus x squared, t equals 2 pi over omega, and then again we have frequency omega over 2 pi, then time period of a simple pendulum t equals 2 pi root L over g, then t equals 2 pi root m over k. Right. Again from waves, velocity of a transverse wave in a stretched string, v equals root t over m. T is the tension of the string, m is the linear mass. And velocity of sound, v equals root 3 r t over m. V equals root gamma P over rho. Here P is the pressure, rho is the density. And fundamental frequency of a stretch string F naught equals 1 over 2L root T over M. F naught V over 4L. Again, for open tubes, F naught equals V over 2L. Then for intensity, I equals power divided by area, intensity level, 10 log I over I naught. Here I naught is the threshold frequency, threshold intensity, 10 to the power minus 12 watts per meter square. Then Doppler's effect, F dash equals F naught velocity of sound relative to observer divided by velocity of sound relative to source. And sonic boom, sine theta equals velocity of sound divided by velocity of the source or the jet. And then a Mach number, velocity of jet or the source divided by velocity of sound. And then again, we have Beats frequency, Fb equals F1 minus F2. These are the basic equations we have from waves and oscillations. There are other derived equations. You should go through all. When you are doing the questions, actually, you will go through all those equations. Alright, students, if you think this is helpful and valuable, share it with your friends. Study together and win together.